When starting the research for this presentation, I initially was thinking of doing it on an alternative interpretation of quantum mechanics called pilot wave theory. Upon looking more into it, however, I swiftly realized that A, I would need to read several thousand pages worth of academic literature in the form of both papers and books in order to get a good enough grasp on the nuances to communicate it effectively, and B, doing a proper presentation about it in such a way as to properly sell it as a reasonable alternative would take much more time than this presentation format allows. Instead, I shall be using pilot wave theory as a way to point out the problems with our current scientific method used in physics in general, and how we as a collective need to change how we treat people and ideas challenging our base assumptions. But first, to go over the orthodox views of quantum mechanics and what they tell us about our world. Quantum mechanics is viewed by the layman to tell us that the world is chaotic, random, and ultimately unpredictable at small scales. This, while true, is a limiting view, so we shall properly call out the base assumptions of quantum mechanics that everything else is built upon. David Bohm put fairly neat and concise words to what exactly these base assumptions are in his 1952 paper titled A Suggested Interpretation of the Quantum Theory in Terms of Hidden Variables, Part 1. So I will be using his same terminology. Bohm identified two base assumptions in the traditional interpretation of quantum mechanics. One, the wave function, with its probability interpretation, determines the most complete possible specification of the state of an individual system, and two, the process of transfer of a single quantum from observed system to measuring apparatus is inherently unpredictable, uncontrollable, and unanalyzable. This indicates that even if we knew exactly the wave function at all points in space, we would still not be able to predict the exact outcomes of any measurements we made, and trying to do so would be a waste of time. The usual interpretation of quantum mechanics has no mathematical issues at this point, and has even been consistent with special relativity since the 1970s. Quantum mechanics is completely self-consistent, and contains no contradictions or internal failings. As Bohm points out, however, this self-consistency does not indicate that the interpretation is correct, saying, quote, "The mere demonstration of such consistency does not exclude the possibility of other equally consistent interpretations." End quote. It is, nonetheless, a fairly accurate predictor of measurements in most scenarios. If you want more detail on all the nitty-gritty bits of the traditional quantum theory, I recommend reading our textbook, Introduction to Quantum Mechanics, 3rd edition, by Griffiths and Schroeder. The usual interpretation of quantum mechanics does seem to mostly predict measurements accurately. Repeat measurements of the same phenomena give data distributions that match up with the probability predictions made by quantum mechanics in most scenarios. It does not, however, successfully predict correct outcomes in all circumstances. It has not yet been made to work with general relativity, failing to give a proper quantum understanding of gravity, and failing to correctly predict black hole interactions. It fails to predict times when charge, parity, and time symmetries are broken. Most egregiously, the base assumptions are fundamentally untestable and unchallengeable. This leads to a serious problem with regards to being able to treat quantum mechanics as a serious scientific field, where, as Bohm points out, the usual physical interpretation, therefore, presents us with a considerable danger of falling into a trap, consisting of a self-closing chain of circular hypotheses, which are, in principle, unverifiable if true. End quote. This then makes it impossible to disprove the usual interpretation within the doctrinal confines of this interpretation, especially because a practically infinite number of slight modifications can be made to the mathematical formulation of the usual interpretation without actually challenging the base assumptions with any inconsistent data. Bohm does point out a potential way to circumvent this critical flaw in the usual interpretation by looking at the consequences of alternative base assumptions to find alternatives that are equally good at predicting phenomena that we can see as the usual interpretation, while still being actually testable and hypothetically disprovable. Bohm settles on three assumptions to use as the basis of an alternative interpretation. 1. That the psi field satisfies the Schrödinger equation, where psi equals r times e to the I s over h bar, with r and s real. 2. The particle momentum is restricted to p equals del s of x. And 3. That we do not predict or control the precise location of the particle, but have, in practice, a statistical ensemble with probability density p of x equals magnitude of psi of x squared. And that the use of statistics is, however, not inherent to the conceptual structure, but merely a consequence of our ignorance of the precise initial conditions of the particle. From these base assumptions, Bohm builds a mathematical framework that contains an additional so-called quantum mechanical potential that is in addition to the classical potential that acts on quantum particles. He then shows that, quote, the psi field exerts a force on the particle in a way that is analogous to, but not identical with, the way in which an electromagnetic field exerts a force on a charge, and a meson field exerts a force on a nucleon. I'm not going to go through his whole derivation of this alternative theory, but I will comment on some of the points that he makes that I especially like. If you want the whole derivation, you can read his paper yourself. Suffice it to say, Bohm concludes, quote, if one makes these special assumptions, our interpretation leads in all possible experiments to the same predictions as are obtained from the usual interpretation, end quote. This means that these alternative assumptions are just as good at predicting future measurements as the traditional ones, while also actually being challengeable. One challenge to this alternative formulation is from the double slit experiment. In the usual formulation, the particle goes through both slits simultaneously, interacting with itself as it does, and destructively interfering, resulting in the iconic distribution that we observe from both light, which behaves more like a wave in this form, and from things classically viewed only as particles, like electrons or neutrons. This destructive interference pattern disappears when one of the slits is covered to isolate only the particles that go through the other slit, so to speak, which collapses the wave function at the slit rather than at the measuring apparatus. In Bohm's interpretation, however, the quantum mechanical potential is the culprit of this odd behavior, and the slit indirectly affects the path of the particle through its effect on the psi field via the Schrödinger equation, leading to the particle being able to reach places with both slits open that it cannot reach with only one, due to the quantum mechanical potential being different in the two scenarios. Bohm then goes on to note, quote, the necessity for this destruction is not inherent in the conceptual structure, and as we shall see, the destruction of the interference pattern could, in principle, be avoided by means of other ways of making measurements, ways which are conceivable but not now actually possible. End quote. Presenting a potential way of actually testing this interpretation against the traditional view in a productive manner. Bohm goes on to analyze the behavior of an isolated general particle in a non-stationary state. After much complicated math that I admit I was unable to follow due to a lack of familiarity with Hamiltonian Jacobi mathematics, he is able to show that the quantum mechanical potential fluctuates in non-stationary states, and the momentum of the particle fluctuates with the same frequency. He also shows that if r is small in these non-stationary states, the fluctuations can be rather extreme, resulting in paths that are highly irregular and complicated, with orbits, quote, resembling Brownian motion more closely than the smooth track of a planet around the sun, end quote. Bohm indicates the process by which a particle could cross a classically forbidden region utilizing this alternative interpretation, whereby the wild fluctuations allow some particle paths to penetrate a barrier, even one with infinite potential, and seemingly tunnel across an uncrossable barrier, while still having a definite position. This interpretation, however, ultimately needs to actually be testable and experimentally contrastable with the traditional interpretation. Bohm proposes a regime where these two interpretations diverge in terms of predictions as a plausible area to look, stating, quote, evidence indicating the need for adopting our interpretation instead of the usual one could therefore only come from experiments such as those involving phenomena associated with distances of the order of 10 to the minus 13 centimeters or less, which are not now adequately understood in terms of the existing theory, end quote. These distances, and the times involved in interactions within them, are small enough to make it a real challenge for us to get great measurements of positions or momenta, or any other pair of similar properties, where failings of the usual interpretation can hide without us being able to notice. Bohm does not actually propose any potential experiments to probe this region and to compare results, but does demonstrate that they aren't impossible with, for instance, an experiment that compares momentum with del of s of x, looking for discrepancies that decay on the order of 10 to the minus 13 over c seconds. A particular theory that gives detailed proposals for the consequences of interactions like Bohm's is pilot wave theory. Pilot wave theory is what is called a hidden variable theory. In our textbook, Griffiths dismisses the possibility of a hidden variable existing and resulting in the weird results of the quantum regime out of hand, stating in chapter 1.2, quote, a particle simply does not have a precise position prior to measurement, end quote, and that, quote, it is the measurement process that insists on one particular number, and thereby, in a sense, creates the specific result, end quote. He does, however, make a footnote acknowledging the existence of Bohm's arguments, but without actually touching on them at all. Griffiths is not in the minority in that regard, unfortunately. Many physicists have been dismissive or openly hostile to hidden variable theories, like pilot wave theory, even since quantum mechanics' introduction. Richard Feynman is quoted stating that the results of the double slit were impossible to explain in any classical way. This, however, has since changed. There have been experiments done by researchers at the Paris Diderot University, among others, with fluid dynamics that result in droplets of silicon oil bouncing on a silicon oil bath and being propelled by the generated waves from those bounces. When not completely symmetrical, these droplets were seen to be propelled by the generated so-called pilot waves. When directed to pass through a pair of slits, in analogy to the double slit experiment, the distribution of droplets match actual double slit experiments fairly well. These droplets can also be led to tunnel through barriers, enter into bound states, and exhibit many other analogous quantum properties, including annihilation from air pockets in the oil bath. When driven in specific chosen geometric regions, like a circular area, the positional probability density of the droplet corresponds closely to the Faraday model of the cavity due to the superposition of all the previous bounces continuing to affect the path of the droplet in minute ways long after the droplet generated those ripples, leading to a fairly unpredictable path taken by the particle. Clearly, then, we now have a potential avenue to explore the quantum realm in exquisite detail through analogy with fluid dynamics experiments. In spite of this clear analogy, reintroduction of this conversation has been quite difficult. Many quantum physicists have been dismissive of it due to a lack of direct evidence of quantum pilot waves. Many other problems that are brought up about it are of the same kind that could have been brought up against the orthodox interpretation of quantum mechanics in its early days, and is developing with much less resources and brainpower allocated towards it. Because it goes against the orthodoxy, however, getting funding or support for research into it is incredibly difficult, and can even risk careers if those questioning the orthodoxy don't have enough academic clout. This persecution comes from an almost religious-like conviction that the usual interpretation of quantum mechanics is the right one, and questioning it is paramount to heresy. This kind of behavior is completely unacceptable in any academic field, and especially so in physics. The whole point of the scientific method is to find the underlying truths about the world around us, and the inner workings of the universe, and that requires questions to be asked. Purposefully forcing people away from potential paths forward for the sake of maintaining tradition or orthodoxy is ridiculous. We should be encouraging ideas that productively challenge our base assumptions, not suppressing them due to insecurities about our theories. We shouldn't be worried that challenges to our base assumptions will result in dramatic restructuring of the theory, because any restructuring that occurs as a result of these challenges will lead to a more complete picture of the physical processes that govern the world around us. An open and honest conversation is vital in maintaining the integrity of the scientific process.